Hello, everybody. Welcome to the first seminar of this year, 2025, which I hope is very happy for all of us. We have this week an invited speaker from the Winnipeg, Professor Jeff Martin. He did his BSc with honors in physics at the University of Manitoba, and then he went on to complete a PhD in physics at the Massachusetts Institute of Technology, MIT, and then postdoctoral work at the California Institute of Technology, Caltech. And then he returned to Winnipeg to take up a faculty position at Winnipeg. Dr. Martin is now the principal or the main investigator in the leader of an international collaboration of physicists, which is going to talk to us. TUCAN, yeah, which is aiming to make the world's best measurement of the neutron electron dipole, not just the best. Okay, this experiment will be conducted at Triumph, yeah, in Vancouver. Recently, he co-authored the Canadian Subatomic Physics Long Range Plan from 2017-21, and he's also a member of the board of directors of the Canadian Institute of Nuclear Physics. And now he has a lot of other expertise in atomic physics, isotope production, lasers, magnetic fields, magnetic sensors, nuclear medicine, nuclear physics, particle physics, physics in general, so atomic physics. Yes, he's going to talk to us precisely about this new TUCAN experiment. And welcome.
Thank you,
Jeff.
Thank you. It's a pleasure to be here. Yeah.
Okay, so
and now I have to walk in the middle. Is that right?
That's right. Raise your hand.
Both hands.
That's it. I think that's
Stick them up. Okay.
Oh, it's not.
It's not working yet.
Again.
So like this, or
yeah.
Oh, okay. Now I see
now
it. Pick me up. Yeah. Okay, it's watching. Yeah, it's watching.
Yeah.
Okay. Yeah. Thank you. It's a pleasure to be here. I've never visited UNAM before, and it's a very nice campus, and I've been very happy with all the people that I've met so far. As said, I'm from Winnipeg. See if I can advance my slide. There we go. Okay. I'm a member and co-spokesperson of the TUCAN collaboration. And so this is a collaboration photo from our last meeting at the University of British Columbia. I show this slide first because at Kokoyoke, I forgot to show it completely. And it has also our funding agencies on it, which is really bad. But also there is the UNAM logo, though. And you'll notice one person in this collaboration. Oh, here she is, Libertad Baryon. And she's making great contributions since joining the collaboration in guiding fields, UCN guide construction, which is being done here at UNAM, and B0 coil construction and UCN source cryogenic testing. And I'll tell you about some of those things today too. I'll start with nuclear alchemy. I came from a nuclear physics conference where we were talking a lot about nuclear astrophysics, and the last real nuclear physics Nobel Prize was to Willie Fowler, and that was for stellar evolution. It's called alchemy. Alchemy is this ancient process where one of the things alchemists were trying to do was turn lead into gold. Well, that's no problem for a nuclear physicist. You just take out this, change the number of neutrons and protons, and then we have gold. And so Willie Fowler was awarded a prize for that. And this is him being presented by the students at Caltech, a nice football jersey with nuclear alchemy written on it. Of how to generate this asymmetry. And the Sakharov criteria are that you need in your particle theory, C and CP violation, baryon number violation, and a departure from thermal equilibrium. Those three conditions are met. then in principle you can generate net baryon number from having no net baryon number. CP violation is the thing that we'll be interested in today for the neutron EDM, and CP is what you do is change all particles into their antiparticle counterparts, but then also reflect parity symmetry as well. And if physics equations are the same, then CP is a good symmetry of nature. Of course, we know that CP, even in the standard model, isn't a good symmetry. But Sakharov noted that something must be different about antiparticles compared to particles. Compared to antiparticles? Whoops, that's a mistake. In order to get something from nothing. So that's the part that the neutron EDM can address. EDM experiments test this symmetry, CP symmetry. Let me just go into a little bit more details about baryogenesis and show you a very simple theory that predicts a baryon asymmetry. Let's consider a heavy boson X, and let's suppose that X can decay to quarks sometimes. Lepton bar, they all have to have different rates. And so I put in different parameters to describe those rates, these capital deltas. And these, the way I've written this, it will violate both C and CP, okay? So the antiparticle will not decay the same way as the particle counterpart. It differs by an amount delta L or 2 delta L actually. But in order to have CPT conserved, you must have that this equality has to hold. You have to have the total decay rate of the X and X bar has to be the same. So that's a second ingredient. And it turns out just by having an initial state that is symmetric in X and X bar production, and then later on you look at all the quarks and antiquarks and leptons that are made by that afterwards, you will find that indeed you have a net baryon asymmetry after this particle has decayed, or sets of X and X bar particles have decayed. And that's how the out of thermal equilibrium Sakharov condition is handled. It's by having this be heavy, so that as the universe cools, then everything eventually decays into quarks and leptons. This is actually coming from a gut baryogenesis model. Not a very favorable model, but at least it shows the idea of why you need baryon number violation, CCP violation, and departure from thermal equilibrium. A more realistic model for baryogenesis is called electroweak baryogenesis. And so it has the same thing going on. In electroweak baryogenesis, it is postulated that the matter-antimatter asymmetry is produced at the electroweak phase transition. And as the phase transition is occurring, bubbles of broken thing happening on the surface that gives rise to the CP violation. So there are some problems though with electroweak baryogenesis. One is that we don't think anymore that the electroweak phase transition is strong enough to have a strong first order phase transition. It's probably second order or higher. And also there's not enough CP violation. And so what people nowadays sometimes try to do is to fix up electroweak baryogenesis by postulating new physics close to the electroweak scale that could, give it this strong phase transition and also give new physics that violates CP. near the electroweak scale. So people try to save electroweak baryogenesis. So just electric dipole moments, how do they relate to CP violation? Well, the Hamiltonian of a neutron in an electromagnetic field can be written in this way in the non-relativistic limit. This second term, which is dn sigma, sigma is just a Pauli matrix, a vector of Pauli matrices dotted into the electric field. That term would violate time reversal symmetry, and therefore by the CPT theorem, it violates CP symmetry as well. So what we're looking for is a small term in this Hamiltonian that has this parameter. So how the experiment works is you put neutrons in a bottle and you measure their spin precession frequency. And normally this would just be Larmor precession frequency, but if you apply an electric field, the precession frequency will change a little bit by an amount, this amount plus 2dn times the electric field. And if you then reverse the electric field periodically, you should see the precession frequency of neutrons, spin precession frequency, change as you do the experiment. The statistical uncertainty of the experiment, the way that we do it, will wind up being governed by this formula. And the main thing I want you to notice about this formula is the factor n, so the number of neutrons that are sensed in the experiment. And that's the main thing that we try to address in our experiment. So it's a precision frequency experiment requiring many, many neutrons. And the way to really improve these experiments is to get more neutrons. Just going back to now EDMs and how they are sensitive to CP violation. So how can an EDM be sensitive to CP violation? It's usually through loop graphs like this one. This is a left-handed down quark changing into a right-handed down quark, but by a loop graph that may contain supersymmetric particles, for example. And so here is a graph showing the phase. This induces a electric dipole moment of the quark that is given by this scale, 1 over the big mass scale squared, and then times the CP violating phase. And let's suppose that there was a theory that had 2 supersymmetric particles in it and had different phases. These are constraints of different experiments on those supersymmetric phases coming from different systems, the neutron, the mercury, and in this particular example, terbium fluoride. And so, and this is graphed for a supersymmetry scale of 2 TeV, coming from Pospelov and Ritz, and then updated by Adam Ritz more recently. So this is sometimes called the CP problem. You can see that basically all of these lines overlap at phases being 0. And so what it says is, well, there isn't any CP violation in the supersymmetric sector. That's sometimes called the SUSY CP. It's near the electroweak scale, though, and that particle in this case is called delta UD. A scalar leptoquark that violates CP could also give rise to a neutron electric dipole moment. Another theory motivated by the strong CP problem and the seesaw mechanism that has 3 additional scalar particles in it, and then a grand unified parity solution to the strong CP problem. So many loops with many particles that have never been seen before. This graph is actually just showing how CP violation in EDMs could be related to other experiments done at the Large Hadron Collider. One of those mentioned is the strong CP problem. That's another problem. There is a term in the QCD Lagrangian that can, in principle, violate CP, and it's called the theta term. And there's a dimensionless constant in that term. It's usually called theta. Naively, you would think it's 1, maybe. Experimentally, we think it's less than 10 to the minus 11. And constrained mostly by the neutron EDM and the mercury EDM. That's called the strong CP problem. When you have a dimensionless constant that is 0 for some reason, there must be a symmetry. And one of the symmetries postulated is the Peccei. A time dependence of electric dipole moments coming from a local oscillating axion field that is the dark matter that's around us right now. And this would give rise to an oscillating neutron EDM. And so people also nowadays search for time varying EDMs of particles like the neutron. And you can also do, in the same experiments, you can also do precision clock comparison experiments. You can also search for mirror neutrons. So there are other exotic ideas of what could give rise to a neutron EDM or be tested in the same experimental apparatus. And so that leads me to this sort of mini summary of the physics of the neutron EDM. Why do we want to do it? New physics for baryogenesis, but mostly for theories sort of like electroweak baryogenesis, I would say. The SUSY CP problem and looking for new TeV scale CP violating physics. The strong CP problem, which is related to Peccei symmetry and axions, and then other new physics scenarios such as time-dependent EDMs and so on. So let me turn now, though, to the experimental situation for the neutron EDM. The current world's best measurement of the neutron EDM is that it's less than 1.8 times 10 to the minus 26 electron centimeters at 90% confidence level. And that's shown in the red dot on this graph over here. Now, this graph is a little bit depressing, I want to express. This is the measurements of the error bar. Called a superthermal UCN source. And so the great hope for this community is that this is just the tip of a big cliff, and we just go to fall off this cliff because we make so many more neutrons with this new neutron source technology. And that's the goal, really the goal of our project, is to make a new way of making very large numbers of ultra-cold neutrons to be used in these experiments using new techniques. And as a result, many groups, as the next stage, are pursuing something like this red dashed line as their proposed error bar, where they hope to get to. And hopefully, also, it's not an error bar anymore, but we make a discovery and we see that it's not 0. That would be really cool. So how do you do these experiments? Well, what you do is take neutrons from a source, ultra-cold neutrons. Now, ultra-cold neutrons are a bit special. You're allowed to put them in bottles like this. And I'll talk about that in a little while, but let's, for the sake of argument, say that I'm allowed to put ultra-cold neutrons there and store them in a bottle just as if they were atoms. And then I just do basically an atomic electric dipole moment experiment, but using neutrons. And I initiate precession in combined electric and magnetic fields. So initially all the neutrons are spin up, but then I tilt their spins down into the horizontal plane, and then they start to precess around the magnetic field that's inside that cell. And they also precess around, well, maybe the electric field that's in that cell. And then after a while, I drain. But the next most important thing for the systematic errors in an experiment like this are to do with magnetic fields. So all of these things that are highlighted here are all to do with magnetic fields. And so we need to very carefully map and understand the magnetic field in our experiments. Ongoing and planned neutron EDM searches. Oh, why do we need another neutron EDM search? There's so many of them. The most recent precise one was done in Willigens, Switzerland. Previous ones were all done at Grenoble. And so they, of course, want to keep doing neutron EDM experiments, but there are others that want to get into the game. What's different about some of those experiments? Well, one thing that's different about them is how they make their neutrons. Do experiments in more clever ways using beams. This is actually how the experiments were originally done, using a beam of particles passing through the apparatus. Now, the most precise experiments are all done using ultracold neutrons. So I'm going to focus on the ones that are up here and just show you a little bit of a few pictures on each one. So the one that has the best limit of the neutron EDM is the PSI experiment. This is their upgrade, and it's sort of like a very large upgrade. There's no size scale on here, but this is something like 5 meters tall. Okay, so it's a very large experiment. Yeah, I wish they had a person there. We're now in 2 cells, one above and below a central high voltage electrode, so that you can measure both electric field configurations at the same time. And then you drain them out to detectors here to measure their phase. So they all kind of look like that. This is the Los Alamos neutron EDM experiment. This is the magnetically shielded room that they have recently installed. And they are also, they have a ultracold neutron source that is under this stack of shielding blocks over here. And they want to measure to the 2 × 10⁻27 level. Some more details. If you look inside their experiment, you see all the same elements basically. So two cells on top of a central high voltage electrode, and then a detector with 2 arms coming out of it, things like that. Pan EDM experiment is done at, it's a Munich-led experiment that's done at the Institute La Langevin in France. Also looks kind of the same, and this is sort of what they're TUCAN Triumph ultra-cold advanced neutron source. And I'll go into a little bit of detail on how we make our neutrons and what's new about this technology. And so first of all, we use a spallation source, which means we slam a very high energy proton into a tungsten target and just blast apart that target into little pieces of nuclei. Once those pieces have too many neutrons, so they start shedding neutrons like crazy. So it's sort of like a fission reaction, but induced by this high energy particle that came in, and that's what spallation is. Then we have a lot of very hot neutrons, and we have to cool them down to become ultra cold. I said we want ultra cold neutrons. And so, well, it's very easy to make them thermal neutrons. You just allow them to interact with materials around the that are at 300 Kelvin, and they eventually come into thermal equilibrium with those materials, and that slows them down. Temperature of about 300 Kelvin. And then you just put some liquid deuterium there. That's another effect that will make them cool down to 20 Kelvin. That's the temperature of liquid deuterium. But what if you want them to be at 3 millikelvin? Well, the way that we do that is we take cold neutrons and they downscatter in a single step process using excitation. Neutron. Well, it's just a neutron that you can put in a bottle, okay? It's neutrons that are moving so slowly that they bounce off surfaces and can be bottled. So typical parameters, they're moving less than 8 meters per second. What's 8 meters per second? Okay, it's 30 kilometers an hour. We know that speed limit. And a temperature of maybe less than 4 millikelvin. And an interesting figure, their kinetic energy is less than 300 nanoelectron volts, not a very commonly used energy, but it's very commonly used for ultra-cold neutrons. When you have neutrons that are moving that slowly, they have very interesting interactions with all the fundamental fields of nature. For example, gravity. If you take mass of a neutron times Earth's gravitational field, you find that the product of those two has this interesting number, 100 nanoelectron volts per meter. Oh, but our neutrons have only 300 nanoelectron volts. So that means an ultra-cold neutron produced here will only go up 3 meters in Earth's gravitational field before it falls back down to Earth. That's really weird for a subatomic particle to do that. Most experiments, they're moving at the speed of light. Okay, so it's not not a very common experimental thing. You can also trap them in magnetic traps using a magnetic moment. And they don't actually, they dominantly interact via the strong force, but you can imagine a neutron that is sort of looking at this blackboard and saying, okay, what does it look like to a neutron? Well, they don't see the electrons in that material, they just see the nuclei. So what they're seeing is a sort of coherent effect where a wave of ultra-cold neutrons is seeing a whole bunch of nuclei. And I like to say that it's like they're lying on a bed of nails. So it's, there's huge space between these nuclei, but the force coherent scattering of them off of that material is what keeps them confined. And then, of course, the weak force. Well, neutrons decay by the weak interaction. So that process has a lifetime of about 15 minutes, which is an interesting human kind of scale as well. So we can sort of put them in a bottle, but we don't put them in for longer than 15 minutes because it would have all. Study the fundamental actions of neutrons. Decay, angular correlations in neutron beta decay. Another really interesting experiment is searching for neutron gravity levels. So imagine you have neutrons of very low energy. Classically, they would bounce on top of a surface like that, but quantum. Now, in the previous BEST experiment, they only detected 15,000 ultra-cold neutrons. So quite a difference. So basically, we're improving N, how many neutrons come out. Even in the next great experiment that those people at PSI will do, they only project that they will have 100,000 ultra-cold neutrons coming out at the end of their experiment. And so this is still a factor of 10 better than what they project. Both are projected numbers, also, I should say. So this is a projection for our source. This is a projection for their upgraded experiments. Anyway, so including running efficiency, we expect we could finish to the 10 to the minus 20, measure to the 10 to the minus 27 electron centimeter level in about 400 days. And so how do these sources work? Or what's so new about these new ultra-cold neutron sources that are just coming on now? Well, how did they used to make ultra-cold neutrons? One way, just use the Maxwell-Boltzmann distribution. So let's say you have cold neutrons at a temperature of about 10 Kelvin. The mean is 10 Kelvin, but you know that there's a low energy tail and a high energy tail. And there's a low energy tail that will always contain some ultra-cold neutron. That was the original way that this ultra-cold neutrons were found. So that they would put, a bottle next to a neutron source and then open the bottle. Oh, there's neutrons in there still, even if removed from the neutron source. And so that's one way. two-state system. It turns out that a neutron in an incident energy of 1 milli-electron volt can strike superfluid helium and create a phonon of exactly the same energy momentum. There's an overlap in the free neutron dispersion curve, energy versus momentum, which follows, of course, the quadratic, shown in the blue curve. And in superfluid helium, that just would have a linear dependence close to the momentum zero state. And you can see that they overlap at a certain point, 1 millieV or 7 inverse nanometers in momentum. And what it means is if you send in a neutron of that energy, it can excite a phonon of exactly the same energy and momentum, and the neutron consequently will just stop dead, stop in its tracks. So that's great. So let's use superfluid helium. And the really great thing about my experiment, we get to play with superfluid helium. It's so much fun. So this is just showing some of the fun things you can do with superfluid helium. This is going through the phase transition, and then the superfluid starts leaking out the bottom through a super leak. This is the fountain effect. This is the roll-in film. So this is a vessel where vessel in a round and drains out no matter what you do. And then this one is showing how heat is transported in the super. There's a normal component and a superfluid component in helium-2, and that's what allows us to transport heat through superfluid helium in our experiment. Where do we get our neutrons? From Triumph in Vancouver. Triumph has a 500 mega electron volt cyclotron and delivers 40 microamp current to our experiment, and it produces neutrons by this. Cyclotron onto a spallation target located underneath this this cryostat that contains superfluid helium. And we use that. This is what it actually looks like. It's under a bunch of shielding blocks. Doesn't maybe look all that scenic, but still it's considered to be a fairly scenic region of our facility. And this is when the prime minister, soon to be former prime minister, comes to town. He stands in front of our, so if he would turn around and look down, this is exactly what he would have seen when he's standing there. And then there's actually a sign here that says ultracold neutrons, which he's just standing in front of. And we used it to make ultracold neutrons. We characterized how long ultracold neutrons can live in superfluid helium. And you can see that keeping them in the superfluid helium for tens to 20, 30, 40 seconds is very reasonable. And then this is just showing how you detect the ultracold neutrons is you just put a neutron detector. And then when you want to sense ultracold neutrons, you just open some valve and neutrons come pouring out. And then you just detect all the neutrons. So it's quite elegant and simple experiment. This is just showing how many neutrons we get when we increase the beam current. Now, this source was uninstalled in 2021 to make way for our new ultracold neutron source upgrade. This is what the upgrade looks like. So again, a vessel containing superfluid helium. It's more horizontal, so this is sometimes called our horizontal source. But there's superfluid helium in all that volume, and then the ultracold neutrons pass out through the superfluid helium and then go into this neutron. Vessel has a sort of structure of different moderators outside it. So neutron moderators like liquid deuterium and heavy water. And then the neutrons pass this way out of the experiment. All the cooling is produced by this helium-2 cryostat. It's actually a helium-3 refrigerator. And here is where superfluid will be up to a level around here somewhere. And this is that tail section. And this is gas systems to control all the helium-3 and helium-4 that is used in our experiment. This is just a neat little movie of us sort of putting the finishing touches. The neutron source is located down in here. These are pumps that provide cooling via the Joule-Thomson effect to the source. And this is just sort of what it looks. This is the last time we saw it earlier in 2024, so spring 2024. And now it looks like you won't even see this. There's more shielding blocks on top of all of this, so it's all underneath concrete shielding. Magnetically shielded room down here that was also, if you watched carefully, it was being constructed at the same time as this actually. And then this is how it looks with all the shielding blocks removed. So there's this big cryostat of big pumps that provide the cooling. And all of that's installed. And we did some cryogenic testing results. And a few things that we discovered. The beam heating and the helium cooling power are in good agreement with expectation. So we're able to systems, well, we had one clog, but it was when we tried to fill the superfluid into the ultracold neutron production volume, and that wound up preventing us from measuring ultracold neutron production. So we attempted to measure how many ultracold neutrons we produced, but we failed. And we believe that that's basically because we know that the helium had been contaminated with air, and we believe that we accidentally put air into the deepest, coldest parts of our cryostat. So there was a frost of nitrogen and oxygen that would scatter away all the neutrons. Unfortunately, it's a very common problem with neutron sources like this. So aside from not measuring neutrons, we did everything else. And our plan is to immediately remeasure this once proton is always off from January to April, and so it'll be April or May before we are able to do this again. And then we're also completing this EDM experiment. This is our magnetically shielded room that I showed sort of the top of before. And we've completed all the magnetic testing of that in September 2024. Professor Baryon was very helpful in all of that, I will tell you. We're doing continued testing and coil installation in 2025. And then we will be putting neutrons into this magnetically shielded room by late 2025. We hope. This is because there is a deadline to finish something before the Triumph long shutdown. Triumph as a facility will be shut down in 2026 for a major construction project, the Ariel facility at Triumph. And then in internal coil systems. So inside this magnetically shielded room, we need a very uniform magnetic field that's produced by this very carefully designed coil. And then we need correction coils to fix any lingering inhomogeneities in this magnetic field. And then one thing Libertad is working on is guiding fields to maintain neutron polarization as the neutrons pass through the walls of this magnetic shield. And then another magnetic thing that we are working on right now is nonlinear magneto-optical rotation magnetometry. This is an all-optical pump probe technique involving alkali atoms. And we've been developing that in Winnipeg over the last decade or so. And we now have 20 sensors that are all installed inside our magnetically shielded room and being tested by my former graduate student, Wolfgang Clausen, who still works on the project as a PhD student at UBC. And this is the timeline. So 2025, we're doing ultracold neutron production. The last remaining cryogenic part that we didn't install yet is our liquid deuterium cryostat. That'll be installed in early 2025 as well. And then we plan to do neutron delivery into the magnetically shielded room by late 2025, before the long shutdown, where we will prepare remaining EDM experiment components and do additional cryogenic testing of the UCN source. And then in 2027, we'll do continue to come to Canada. And Mexican students are eligible. And we've hosted at least 2 Mexican students at University of Winnipeg, both in physics, at least 2, because I know there are 2 of them in physics. Of course, all kinds of physics projects are available. You don't necessarily have to work for me. You don't necessarily have to work at University of Winnipeg, but if you need someone to be your supervisor, I'm happy to do it. Students receive funding. Airfare to the internship is only something like 12 to 14 weeks, something like that. But students get funding to come to Canada, stipend for housing and food, and even health insurance for emergencies, and go there. If you'd like more information, or if you have any students that are interested in this, please contact me and I'll help you figure it out. University of Manitoba has a graduate school. That's where I'm at University of Winnipeg, but there's a nearby university called University of Manitoba that has a PhD program in physics that's how I supervise graduate students. This is where you go to more information about that. They have if you go to that website, you'll see the steps to follow. Project at UBC or SFU or University of Saskatchewan and other Canadian institutions, or institutions in Japan if you want. And that brings me to my conclusion. So neutron EDM carries a strong physics interest, and it places a tight constraint on CP violation, to particularly strong constraint when the new physics couples to quarks or gluons. And it's this is in a highly competitive field with many new ideas and technologies. Mainly to do with the UCN sources. And the next generation of experiments are aiming at 10 to the minus 27, an order of magnitude improvement in the uncertainty. And it's mostly coming from these new neutron sources. And we're one of these several experiments. And our unique thing is that we have this unique ultracold neutron source technology with the potential to be a world leader. And expect more updates and results from us very soon. Thank you.
For an excellent seminar, Jeff. Are there any questions?
Eduardo, so what do you mean by very The other two experiments that you mentioned at the beginning. Is it the same?
Right. So I can give you. So what I mean by soon is at least we're turning on our neutron source again in a few months, and we're going to see lots and lots of neutrons. In that. And then ultimately, though, you saw that we were measuring beyond, in 2028 and beyond. You want to know when are we going to have a neutron EDM result, right? So probably have some results from these runs in 2027, but probably only at about the same level as has currently sort of the. So that. And other experiments, I don't want to scroll all the way back, but anyway, the Los Alamos, most of the other projects, they have a neutron source already operating, whereas we're upgrading. And so those numbers that I showed for how many neutrons they will.
In the systematics, I'm guessing you are measuring the magnetic dipole moment to understand the deviations from the right?
Correct.
So assume how you the measurement of the magnetic dipole moment?
No, no. No, it turns out to do that, you usually use a cell. So one of the systematic errors systematic/statistical errors in this experiment is there's a gravity distribution of neutrons. There's actually fewer neutrons at the top and more at the bottom. So different energies of neutrons actually have different distributions, density distributions in the cell because of gravity. So slower moving neutrons are sort of more at the bottom, and faster moving neutrons are more at the top, or evenly distributed at least. And so that gives rise to a systematic error where you're measuring different precession frequencies. If you use a smaller cell in height, then you can do better on that. So you'd want to develop a dedicated experiment. And it turns out that quantity, the neutron magnetic moment, has been measured very precisely. So it's hard to imagine doing much better on it. So it's we're doing a relative measurement basically. So we do always measure that, but it's sort of, we see it bounce around because the magnetic field is always sort of bouncing around, but then the magnetic field changing, and so we back that out and cancel that out.
And also in this contribution, you have a plus minus sign, right?
Yes.
So
yes.
Are you able to discriminate on that?
Yes, well, the plus and minus is meant to indicate the reversing of the electric field in the experiment. So we do one experiment where it's plus, and we do one experiment where it's minus, and we are always comparing those two answers that we get. So that's the signature is, we're measuring, a magnetic moment that's up here, and then a magnetic moment that suddenly goes down here when we change the electric field. Oh. That's what we hope, a precession frequency.
And just a general question on, you mentioned that for the standard model, you have 10 to the minus 3 watt.
Right. And one version of, depending on what you mean by standard model, but yes. That's the CKM contribution. There's also this. non-zero neutron EDM at about the 10 to the minus 27 level, of course, just below the experimental precision. And this one in particular solves electroweak baryogenesis as well, or solves baryogenesis. So, and it's very similar to electroweak baryogenesis, but there's this other, something happens after the sphalerons in electroweak baryogenesis sense. And that it's a very sharp phase transitions, and somehow this new particle is involved in that as well. And that's what gives rise. So there still is some room to explain electroweak baryogenesis using, something that also predicts a non-zero neutron EDM within reach. Of course, you can always solve electroweak baryogenesis by pushing up the scale of this, of the new phase transition. If that happened at a higher scale, then we would, we wouldn't see it, or we'd have to measure much more precisely, or some. But then you have to say, well, why is that new scale? Like, the theory would have to motivate that in some way. Thanks.
Very basic one. How polar can you go? I mean, it's easy to, go colder and colder, and then reduce the.
Well, this one experiment that I mentioned, that is the one that's bouncing. Yeah, this one where you bounce them off of a mirror, and then confine them by gravity. The energy scale is pico electron volts. Wouldn't it be great if you could have pico The way they actually do that experiment is they shoot neutrons in sort of horizontally. So they have nano electron volts energy in this direction, but then picovolts in this direction. But could you do better? I honestly don't know, and I kind of don't think so. And the experiment that would be motivated by that, though, would be something like this, I think, where you have gravity levels of that. It's a really interesting experiment, again, because it's picovolts on this scale, and the height is actually quite large, so 30 microns, which is huge. So you have a really large quantum state that can be almost imaged, right? So yeah, if you have that the motivation of the strong CP problem, that is actually within the standard model as well. But I think even this theta being reduced so much, even that there has to be some new physics wrapped up in that somehow, I think. So I do think that it's really something new if we do discover a neutron EDM.
Questions? I have a practical question. How do you get the deuterium?
Deuterium, it's just from bottles. Yeah.
Yes.
Yeah. Household deuterium. One interesting thing about Canada is we have a lot of heavy water. It's used in our nuclear reactors, so the CANDU reactor. You might know that and we paid for ours. Because we're going to irradiate it.
Okay.
And the deuterium, I suspect, comes from sort of the same source, actually. Yeah.
Questions? If not, let's thank Jeff again.